Hello Math 122, this is the video for section 5.4 all about interpretations of the definite integral. So we're going to get started with some notation for definite integrals that we've talked about before, but hopefully give some motivation for why we choose this notation. So remember that with derivatives, we had Leibniz notation, which looked like dy over dx for the derivative. And the purpose of this notation is to remind us that the derivative is ultimately just the quotient of differences. So it's the quotient of the change in y over the change in x. And the notation that we use for the definite integral, this definite integral from a to b of the function f of x, also has a purpose to remind us that the definite integral is ultimately just a limit of Riemann sums. So how do we interpret this as a limit of Riemann sums? Well, the dx that's showing up inside of the integral can be thought of as a small change in x, similar to the delta x, the same way that in the Leibniz notation, the dx showing up in the denominator can be thought of as a small change in x. And then this product, f of x times dx, that looks like the terms f of x times delta x that are showing up inside of the Riemann sum. So we can view this definite integral from a to b of f of x dx as an infinite sum of these small terms f of x times a small change in x. And the reason that this notation is important is because it allows us to understand the units of these integrals once we take them. So the unit of measurement for a definite integral from a to b of f of x dx is just the product of the units for f of x and the units for x. So remember that for derivatives, the unit was the unit of y divided by the unit of x. And in this case, because we have f of x and it's multiplying dx, this time it's the product of the units for f of x and the units for x. Okay, so some examples figuring out what the units would be for some integrals. Let's say that the units of x and f of x are both centimeters. Then, using this rule that I have in the box, the units of the definite integral are going to be centimeters squared. And this intuitively makes some sense because we know that the definite integral from a to b of f of x is going to represent some kind of area. So we talked about that in the last video, that this definite integral measures the area between a curve and the x-axis, counting certain areas above the x-axis as positive and other areas below the x-axis as negative. But regardless, it's going to calculate area in some way, and we know that the units for area are going to be centimeters squared if we're measuring length in centimeters. Okay, and another example we've talked about, if we have a function v of t, and this function gives us velocity, say in meters per second, and we'll say that t is time in seconds, then the units of the definite integral of v of t dt are going to be meters, because meters divided by seconds times seconds is just going to give me meters. And again, this intuitively makes sense because all the way back in section 5.1, we said that this integral, the Riemann sums of v of t, represent the change in the position of whatever object is moving with that velocity. So if we're looking at change in position, the way that we would measure that is going to be some kind of length measurement. In this case, we're using meters. So again, intuitively, this kind of checks out. And then maybe just a previous result to remind you of before we get going with a bunch of different examples. If we have a function f of t, and this function gives us the rate of change of some quantity with respect to time, it doesn't matter what that quantity is, then the definite integral from a to b of the function f of t is equal to the total change in that quantity from t equals a to t equals b. So let's look at an application problem related to the definite integral. In this first example, we have a bacteria colony that starts with a population of 14 million bacteria, and t hours later, the population is growing at a rate of f of t equals 2 to the t million bacteria per hour. So we'll ask two different questions related to this problem. So the first one, we want to give a definite integral that represents the total change in the bacteria population from t equals 0 to t equals 2. Well, remember from this previous result that if we have a function that gives the rate of change, the definite integral is going to represent the total change in that quantity from t equals a to t equals b. Okay, so if we want to find the total change in the bacteria population, then we can take the definite integral from t equals 0 to t equals 2 of the rate of change function, which is going to be f of t equals 2 to the t. So we have 2 to the t dt. So this definite integral here is equal to the change in population between t equals 0 and t equals 2. Okay, so that's the answer to the first question. Now we can write down a second question. Let's say we want to find the actual population of the bacteria colony at time t equals 2. So remember, this definite integral from 0 to 2 is only telling us the change in the population. It's not actually saying anything about what the population is, but we can use the change in the population and this initial population, the fact that we're starting with 14 million bacteria, to figure out what the population is at time equals 2. So first off, we're going to take this integral from part A and we're going to plug it into a calculator. So now that I'm in Desmos, I'm going to type in this definite integral. We have the integral from 0 to 2 of the function 2 to the t dt, and Desmos tells us that this is about 4.328. So back in OneNote, we found out that this integral from 0 to 2 of 2 to the t dt was equal to 4.328 using Desmos. Okay, and the bacteria population began at 14 million bacteria, and it increased 4.328 million from time equals 0 to time equals 2. And therefore, we can say that the population at time equals 2 is equal to the 14 million that we began with plus the 4.328 million that we had from time equals 0 to time equals 2, that change, and we get 18.328 million total bacteria in the population at time equals 2. So the important thing to note here again is that the definite integral does not necessarily tell us what the population is at time equals 2, but it tells us what the change in population is from time equals 0 to time equals 2. So if we add it to the initial population, that's how we can get the actual population at time equals 2. So this next example is mostly going to be conceptual. Let's say that we're given two different plant species, and we have the rates of growth of the populations of these two plant species measured in new plants per year, and they're given by these two graphs that I have here in the plane. So species 2 is in blue and species 1 is in purple. Again, on the vertical axis we have new plants per year, and on the horizontal axis we have the number of years, and assume that the populations are equal at time equals 0. The question is, which population is larger after 1 year and which population is larger after 2 years? So the first thing to note here, note that both functions represent a rate of change. And specifically, it's the rate of change of the population of the plant species. So the rate of change of population. So if we want to find the total change in population, we need to take a definite integral of the rate of change function. So we're trying to figure out which population is larger after 1 year, which population is larger after 2 years, and we assumed that both of the populations are going to be equal at time equals 0. So really, at least if I'm looking at which population is larger after 1 year, I'm just asking the question, is the definite integral from 0 to 1 bigger for species 1 or bigger for species 2? Because that's going to give me the total change. So let's look at the definite integral from 0 to 1. And maybe I'll call this function for species 2. Maybe I'll call that f sub 2 of t. And I'll call the function for species 1 f sub 1 of t. So after 1 year, if I want the total change in the population of species 1, I'll put in an f sub 1t here, dt. So this is the total change for species 1. And this integral from 0 to 1 of f sub 2 of t dt is the total change for species 2. So if I want to figure out which one is bigger, well, let's go up to the functions and determine which area is bigger. So if I look at species 1, the purple function, the area under that graph from time equals 0 to time equals 1 is going to be bigger than the area under the blue curve representing species 2. So in this case, the integral from 0 to 1 of f sub 1 of t dt is bigger than the integral from 0 to 1 of f sub 2 of t dt. And since the populations are equal at time equals 0, we can say the population of species 1 is greater than species 2 at time equals 1 year. Okay, and for the second question, we asked the same thing, but this time we're looking at 2 years. So which population is going to be bigger after 2 years? Again, the interpretation is just going to be the area under the curve for species 1 and for species 2. So we're looking at the integral from 0 to 2 this time of species 1. And we're looking at, again, the integral from 0 to 2 for species 2. And we want to determine which one is bigger. So in this case, going back up to the functions, so if I look at going from year 1 to year 2, now the rate of change of species 2 is much bigger than the rate of change of species 1. And in fact, it's big enough that this area between species 1 and species 2 is going to be bigger than the area from time equals 0 to time equals 1. So if I look at from 0 to 2, now the area under the species 2 curve is going to be bigger than the area under the species 1 curve. So I'll write that down. The definite integral from 0 to 2 of species 2 now is bigger than the definite integral from 0 to 2 of species 1. So at time equals 2 years, the population of species 2 is bigger than the population of species 1. So in the next example, we again want to interpret the definite integral. In this case, we have the integral from 0 to 5 of s of x dx, where s of x is the rate of change of salt concentration in the units of grams per liter per centimeter, and x is the depth below the surface of water in centimeters. Okay, so first off, let's start with the units of what this integral is going to be. So the units of s of x are grams per liter per centimeter, and the units of x are just centimeter. So the per centimeter and the centimeter are going to cancel with one another, and we get grams per liter, which is just the unit of the salt concentration. So I'll put grams per liter is unit used to measure the salt concentration. And because s of x is a rate of change function, this integral from 0 to 5 is going to give us the total change in salt concentration from a depth of 0 below the surface to a depth of 5 below the surface. Okay, so the integral from 0 to 5 of s of x dx represents the total change in salt concentration from 0 centimeters below the surface to 5 centimeters below the surface. All right, and for the last example, we have some graphs that give us the velocity of a particle that's moving on a number line. So this particle can only move to the right and to the left. It's one-dimensional motion here. And we say that the velocity is positive when the particle is moving to the right, and the velocity is negative when the particle is moving to the left. And in each of the three different cases that I want to calculate the change in position of the particle from time equals 0, the initial position, to time equals 5. And it's going to change depending on what the graph of the velocity function looks like from time equals 0 to time equals 5, but we'll calculate it in each case. So remember, the velocity is a rate of change function with respect to time. So if we want to find total change, we take the definite integral from t equals 0 to t equals 5 in each of these cases. So for the first one, the total change in position is going to be equal to the integral from 0 to 5 of v of t dt. And this is actually going to be the case for all three different velocity functions here. But in this case, the velocity function is just constant at -3 meters per second from 0 to 5. And this definite integral is going to give us the area between the velocity function and the x-axis, where it's negative this time because v of t is always negative. So I would write the integral from 0 to 5 of v of t dt is equal to -3 times 5, which is equal to -15, and the units are going to be meters, because we are working in meters per second. So meters per second times seconds is going to give us meters for our units here. Okay, in the second case, again, the total change in position is going to be equal to this definite integral from 0 to 5 of v of t dt. And in this case, this definite integral is going to be equal to the positive area of this portion, shaded in green now, and the negative area of this portion added together. And this is going to give us a 2 times 3 for the first portion, and then it looks like we have a -3 times 2 for the second portion, and this gives us a 6 minus 6 equals 0 meters. So in this second case, the particle is going to end at the exact same location it started. There's no net change in its position. And finally, this last one, again, the total change is still going to be the integral from 0 to 5 of the velocity function, but the velocity function is different again. And this time, we calculate this area under the velocity function by using the formula for the area of a triangle. So it's positive here because the velocity function is always positive. And we get that the area is 1/2 times the base, which is 5, times the height of the triangle, which is 10, and this gives us 25 meters. So at the end of 5 seconds, the particle is going to end 25 meters to the right of where it began. And I don't know if I said this in the first case, but for part A, since we got -15 meters, the particle is going to end -15 meters to the left of where it began at time equals 0, wherever that was. Okay, so that's the last example for this section. Ultimately, most of these problems for this section are just different ways to interpret the definite integral and make sure that you understand units. So hopefully this was helpful and this is enough information for you to do your homework.